So, for the next part of the assignment, we need to investigate the phenomenon caused by fuel rod reweighting and quenching using a rewet facility. So we will have to simulate one out of 3 fuel rods using in this model. So this phenomenon is mostly related to the lack of coolant, loss of coolant accidents. So when we don't have any coolant in the reactor core, but we still have a decay heat, our fuel rods starts warming up really fast, quite fast to really high temperatures. And even if we inject some water, it will not cool down very rapid at the beginning because of the critical heat flux. It will start the film boiling. So then we will have to wait some time until the fuel rod surface cools down until the minimum film boiling, and then it starts to removing heat with a higher efficiency. So in this case, in the trace model and trace simulation, we will have to follow this quench propagation along the fuel rod, and also to analyze the behavior of the fuel rod temperature. So nowadays, chemical engineers, they try to make kind of balance to modify the coolant somehow to increase the speed of the quenching front propagation. But it also the balance between like cooling down, and the same time, if you make the quench front propagation very fast, it can lead to the kind of shock wave, because when the water touches the surface of the really hot fuel rod, so then it starts evaporating. So a lot of boiling, a lot of vapor will generate really in a short time period, then pressure goes up. So they try to balance. In this case, we just use a pure water. The quench propagation not so fast. It will be noticeable in a trace simulation. So, and there is no problem. We don't have to go for deep time steps. It will be enough to use time steps with a size of 1 second or even more. So first we need to run the model editor. It will take some time. I just upscaled the interface. I hope it will be much clear for you what happens on the display. I hope so. So first we need to create a new file, a trace model. Yeah, I think it is better. So the model in our case will look like that. It is a central pipe with a inlet, outlet, and 2 heat structures. They will be different colors, but we have a quite cheap projector. I don't know why the colors are different, but still. This heat structure represents the fuel rod inside the glass tube. This heat structure will represent the glass tube wall, which connects to the atmosphere, since we need to take into account the heat transfer between the glass tube and the atmospheric air. So they have 2 boundary conditions, like inner and outer. In case of the fuel rod, the inner radius is equal to 0, so we don't have an inner boundary condition. We will have to only outer, which is connected to the internals of the glass tube, and the outer boundary, outer heat structure will have both boundaries, inner and outer. Inner boundary will represent the surface between water and vapor and glass, and the outer boundary between glass and atmospheric air. So then we can start modeling with creating pipe. Oh no. First we will just modify the time step data here. Since we need to make a simulation for 500 seconds, we will do this at the beginning just to not to forget it later. So change it to 500 and press OK. So then we need to create a hydraulic component pipe. If you click on the field, it will show you the parameters which you can choose. So the total length of the pipe is presented in an assignment instruction. There are a few tables with the initial parameters of the coolant, of the glass tube, and the fuel rod. So here we have a flow channel length is 2,185 millimeters. So it is 2 meters, 185. Hydraulic diameter has to be calculated. Since we have a kind of tube inside the tube, internal heat structure goes in the axial direction inside the glass tube. It takes some space inside, so it reduces the hydraulic diameter. It is also shown here, this picture. Since we have a glass tube and a fuel rod inside, we need to calculate the hydraulic diameter, but it is easily calculated by the formula. We can just take outer radius minus inner radius and times 2. It is a hydraulic diameter for the case in pipe inside the pipe. So I have already calculated it somewhere. I just need to here. It is 0.01195 meters.
Excuse me, could you repeat the equation again? The equation.
It is just outer radius
minus
inner radius and times 2. It is in the
times 2 in the bracket, like the difference times 2.
It is in the bracket.
Okay.
Times 2, I mean, to invert radius to diameter.
Yeah. Okay.
So number of cells for my simulation, I use 20 cells. We have one pipe and it is a vertical one. So we need to choose the orientation to the vertical and just press OK. It is really small. We need to make it more clear. We can make a scale drawing and just to make it a bit longer and wider.
500.
Like that. So then we need to set the initial conditions for the pipe internals. They're given in tables, in assignment instruction. So we have a coolant temperature, we have a steam temperature, and like fuel rod temperature, but it is for the heat structure. We are mostly interested in pressure and the temperatures. So then, since the pressure is 1 bar, it is 101.325. It is atmospheric pressure, or we can just define this like 100,000 Pascal. So then we need to change the liquid temperature and the vapor temperature. Go back. For the liquid, it is 318 kelvins and 400 for the steam. 318 and 400 for the steam. And first of all, since we don't have any water inside the glass tube, we just change the gas volume fraction to 1. We have a steam only. So then the initial parameters for the pipe are already modified. We just need to make a few changes here in the modeling. So we can go, we need to set the pipe type here. It is a default one, no accumulator. We just need to change it to model 7, pre-flood heat structure. And here is the one unknown variable for the pipe. We need to define it is unheated fraction. So based on the parameters in the table here, our length of the glass tube is 2000 and something. Heated length of the heating rod is 1550. So we just need to calculate the fraction of heating rod to the pipe by the length. So
The difference.
Since it is unheated fraction, it is just 2185 minus 1550 divided by the total length of the pipe, and it is also equal to 0.29. Also, since we have to connect the heat structure, here, 0.20, heat structures to the pipe, we need to have a kind of well modelization, since it connects not like object to object, it connects node by node between the objects. The length of the nodes of the cells should be exactly the same for the heat structure and for the pipe. And also, we have one initial condition is that the heated section starts from the bottom in the 470 millimeters. To make it easier to calculate everything later, we can remodelize the pipe with and change the cell size to make it like 470, then 1550, and the rest. I don't remember how much. So we just need to click on the component geometry cells and change the size of the cells. They're going from bottom to the top. So I have my own pre-calculation, but you could do your own. You can divide in a different amount of cells, not exactly 20, 40, 100. It depends on the accuracy needed in your calculation. For this case, 20 is quite enough from my point of view. So then, for example, for the first 4 cells, I defined the length as a 0.1175. So these 4 cells are exactly 470 millimeters. So then, for the next 13 cells, the cell size remains the same as it is the default one for this model, for 20 cells. I just modified one to make it more precise to the heating rod structure. So the last cell of the heating rod will be 0.12975.
0.112.
So then our pipe became longer than it was supposed. It is 2.20, almost 24 meters. It should be shorter. So then other
it's just
2 cells, we need to reduce the size of these cells.
This one is
So then we just change it to 0.0825.
these 2.
So then if you go down,
This one.
the total length of the tube remains the same as it was in initial conditions in the table in the assignment instruction. Volume area or flow area is calculated and volume are calculated automatically. So since we don't change flow area, it just calculates the volume for our case, since we have chosen it is the default option that it takes flow area and calculates the volume. We don't need to change anything else. So, and then we can close it. Everything is done for the pipe. For the pipe, next part will be to create field and break component. It is an inlet and outlet respectively. we just need to go to the hydraulic components and then choose the fuel. There are a lot of unknowns we will have to define, but they are given in, most of them are given in assignment instruction. We just need to change the fuel type to the constant mass flow. It is the second option. So then length and volume, it doesn't matter which one you will use, but I would recommend you to use the dimensions to represent kind of extension of the pipe. Since you know the diameter of the pipe, you can, if you define the length, like 0.1 meter, 10 centimeters, you can calculate the volume. You know diameter, you know length,
And just multiply.
so then you just calculate the volume.
Okay.
So for this case, if we use a 0.1 meter length for the fuel component, so then
You can do the geometry.
we can use the volume, define the volume. For this case, it is really small value in cubic meters, but it will be 0.0000 zeros and 112,157. Yeah, in cubic meters, it is a really small value for this diameter. And press enter.
Okay.
So then we need to set the initial conditions like liquid temperature, initial vapor temperature. They're exactly the same as for the tube. It is for 318 for the liquid and 400 for the vapor.
Show 1 bar. Show 185.
400 for the vapor. And the initial pressure is atmospheric. 101,325. So for the fuel component, I think that everything is done. Initial gas volume fraction is equal to 0. It is filled by water. To just to avoid the delay between, like if you define it as one first inlet, since fuel component has its own volume, it will fill the fuel component and then
Just the pipe.
then just the pipe. You're right. So then we can leave it as 0. One thing we just need to do is to connect this fuel component to the pipe. Click here on top of the connector, click on the outlet of the fuel component and the inlet of the pipe. Since it is connected to the end of the pipe, we don't need to define the cross connection angle, so it is kind of 180. So next part is a brake component. Since we have to have an outlet, then go to hydraulic components and brakes. Click on the field. Also, we'll have to define some parameters. I would say that we can use the same length and volume for the brake component as well. 0.1 and oh my god, 0.0000 111,157. Or you can just copy from the fuel component. In this case, the gas volume fraction will be equal to 1. On the top, we have a
1.
we have a pipe filled by pure vapor. In this case, we don't have non-condensable gases. It is also possible to simulate the non-condensable gases presence using trace code, but in this case, we don't need for that option.
That one is
So
400.
then, initial mixture temperature, we can define it as like 400 kelvins, since it is a vapor. If we define it less than 400, then the density will be less, it will go down to the pipe. Or the density will be higher, it will go down to the pipe. We don't need for that. We can define it at 400. since we have a cross flow pipe of the vapor, while we don't have any coolant inside. Our coolant is vapor. It is quite poor coolant with a low heat transfer coefficient. So we can define it as a 400, and initial pressure is also atmospheric one, 10325. So it's done for the brake component. We just need also to connect this one to the pipe. The same procedure as the previous for the wheel component. And the next stage is creation of the heat structures. If you press this button, here on the bottom you will have a thermal heat structures. There are two ways to create the heat structures. It is this way, or if you right click on the pipe, and there will be an option. If you click on the pipe, here will be edit heat structures in new. But in this case, you will not have a graphical representation of the heat structure, so then I think it's better
just there.
for the study purposes. It is better to represent it like graphic. For this case, we have a cylindrical heat structure. So we have a fuel rod simulation. The length of this heat structure should be exactly the same as the last pipe, which is 2.185, if I'm correct. Inner radius is equal to 0, since we have a fuel rod. We don't have any inner flow path. So, and the thickness is also
Rod diameter.
shown
Radius.
in the table here. Heat and rod diameter is at 12.25. Since we need to define the thickness, it is a radius.
Okay.
So then
6.
you need to divide this value
1 to 5.
and also to convert it into meters. Okay, 0.00615. Fuel rod temperature is also presented in the table. Here it is 793 kelvins. 793. And also material. In such a case, we use, it should be somewhere.
Material number 5.
Huh?
Material number 5, it's right there.
Yeah, I hear it. Yeah, see, material number 5 is used for this case. It is this one. You just need to choose it and press OK. And then axial cells and radial nodes. Since we have a pipe with the 20 cells, we need to make this heat structure with exactly the same amount of cells. Radial nodes, it depends on, also depends on the accuracy you need in your case. You can check the temperature of the fuel rod, for example, inner surface, central surface, and outer surface. If you have just one radial node, it will be more or less homogeneous temperature across the whole fuel rod. So then, if you divide the fuel rod, for example, into 5 radial cells, it will be like layer by layer temperature. It will take into account the thermal conductivity and so on. So then you will be able to analyze the central rod temperature and the outer surface temperature, and also, it is possible to check the temperature layer by layer. It is for separate investigations. For our case, 5 nodes, radial nodes is quite far enough. So then we just can press OK. Yeah, here is the heat structure. In your monitor, it is probably a red color. So here it is a white one. Doesn't matter actually. For this heat structure, we just need to remodelize it the same way as we did for the pipe. now it is 20 cells heat structure, but the notarization is equilibrium, uniform, cell by cell. We need to go to axial properties. Here is an axial length. But for the heat structures, it goes from top to the bottom. So the first cell, by any reasons, on top
It's the bottom one.
instead of bottom. But the first one is on the bottom of the heat structure, and the last one on the top. I don't know why they inverted this. So then the same sizing, like for the first 4 cells, it is 0.1175. So next 13 points are the same, 13 nodes are the same, only node number 18 is to be modified. So then this length is 0.12 and 975. And the last 2 cells are 0.085. And then you can just close it. One more thing we need to modify here is the fine mesh count. It is the option for each block models. It is 8 increases the kind of internal meshing of the few rods. We need to define it as a 3. Honestly, I don't remember why we use exactly this value, but for maybe after the lot of iterations, so the behavior is more or less the same as the actual test facility. So then we can define the average rod mesh count as 3, and just close it. Then we can also change the, if you don't have few rod option, it's not a few rod. We don't need to modify all the parameters for related to the reactivity coefficients and so on. Axial plane Z direction, and then we can go to the radial geometry. So everything is defined well. For each radial node is the same material, so we can also double check the parameters here if we need that. So also if we go to the axial node and surface boundary conditions, here is a definition of the inner surface boundary condition and outer surface boundary. We don't need to modify it because it will be changed automatically when we connect our heat structure to the pipe. There is also option to the re-analyze. It will change the size of the cells automatically, dependently on the sizing of the target object, but we did it already manually. Sometimes it makes it in a quite weird way. I don't usually use it. It works sometimes, like 9 out of 10 times it will be correct, but this one you don't know how to explain when it happens. So it will connect by the outer surface to the tube, and then starting cell for the heat structure is first out of 20. It will connect from the first to the last one. And then the hydrocell, it is a hydraulic component which we are connecting, It starts from the first and then ends to the next. You can inverse it. You can connect cell number 20 from the heat structure to the cell number 1 of the pipe if you need to just invert it. Okay, so and just press OK. Also, one thing we need to change for this heat structure. This size is quite difficult to find anything here. We just need to define the axial conduction as true, and we also need to set the axial conduction. Axial conduction is true, and fine mesh flood is true as well here. So as far as I see, everything is done for this heat structure. We also need to create the second one for the outer surface, for the glass tube. Just click here, thermal and heat structure. So then it will save the parameters from the previous one. We just need to use this one as a length. It is the same as the pipe length. Thickness is represented in the table. Wall thickness is, as far as I remember, 3 millimeters. Yeah, 3 millimeters. 0.003. Inner radius is the radius of the pipe. So then you just need to divide here. It will be 12.1. And the temperature, we can assume that it is equal to the steam temperature as a 400.
For the radius, shouldn't it be in meters?
Yeah, in meters. So
0.112.
and temperature is 400. Axial cells is 20, radial nodes, we can also leave it as 5 or even reduce it like to 4 or 3. It will make calculation a little bit faster. These heat structures usually take a lot of computational power, and the more radial nodes, the more axial cells, and also you can make kind of system multiplication of the heat structures. Like here, it is represented as 1, and here's a surface multiplier. You can build 1 and multiply it by like 70, 100, 1000, depends on how many heat structures you want. For reactor core modeling, you can multiply it like by 12,000 to represent each fuel rod inside the reactor core.
The material is the same.
No, we will modify material.
Okay.
We need in a common and basic database. We don't have a glass.
Yeah.
We will have to create a new material manually. So then we just need to go to on the left side to the thermal and use the defined materials. Right click on that and press new one. It is unnamed, you can rename it as a glass, whatever you want. And here is on the bottom you see material properties table. If you click on that, there is a table with 0 rows, you can add 1. Or if you need to make a simulation of using the materials with the temperature dependent parameters or like pressure dependent, so then you can add as many arrows as you want to make it like temperature dependent parameters as it is. Then it will take points like for 200, 300, 400 for example kelvins, and then it will interpolate the values between these points, and we'll use these parameters in the simulation. But in this case, we don't need to follow this change of parameters for the glass. our temperature range is not so high, and we can use the parameters defined in a table in an assignment instruction. So basically it is 273 Kelvin, 2273, 2230 for the density. Specific heat is equal to 750. So then thermal conductivity is 1.14. And the emissivity is 0.93. Then just press OK, and all the parameters will be defined for these material. Then we just need to click on our heat structure and go to the radial nodes, radial geometry. Here we can define our material. So now we have a user-defined material, glass. Just choose this material and press OK. It will define this material for all the nodes, all the radial nodes for our case. And then just press OK.
Or is it the same color?
So, since I forgot about one thing again, it is a radial or axial renodalization, the same procedure as we did for the previous heat structure, but here, for the first 4 cells, is 0.1175. So next 30 are the same as it was, then 0.12975, and rest 2 points, 0.0825. So we don't need to change any other parameters. We just those. Again, check that the fuel rod option is not a fuel rod. I will check briefly about the first heat structure. Does it have to be defined as a true? No. So then for this heat structure, I think everything is done. You should take videos and only one thing. We defined this already here. Temperature. Yeah, it is a default one, 400 for all the cells. You can, since we know the outer temperature for the atmospheric air, it is 300. You can take here 300 for the outer node and then just something intermediate values, but we can use 400. It will cool down quite fast, and since do you remember for the radial nodes for the glass tube, have you defined like a 400 as a steam temperature, or made like 300 for the outer and then just scale down?
Yeah, so this is glass material. I think it doesn't have so much importance here.
Yeah, 3 millimeters of glass.
Yes,
It will,
it cools down.
with since it has a really high thermal conductivity in comparison with air, it will take it.
Maybe the inner surface is as hot as the steam, and then
Steam, and then just couple degrees
and then it goes.
Yeah, it goes down, but I think since the thermal conductivity and heat transfer coefficient of the air is quite low, so then we can define this at 400.
Yeah, I think it will calculate anyway
Yeah, yeah.
right values, so probably
then-
doesn't matter too much.
Then press OK. We don't need the axial conduction in this case since the thickness is just 3 millimeters. So we don't take it into account just to reduce the computational power. Fine machine flux, we don't need that. So we don't have any gas gaps to define the heat transfer coefficient. Only one thing is that we have to define the outer boundary condition. Here in the axial nodes and surface boundary conditions, you can click here and you see on the right side the outer surface boundary condition. You can easily choose all the cells and then for the outer boundary condition just to change to the constant heat transfer coefficient and surface temperature. So then we need to define two parameters. Sink temperature, it is atmospheric air temperature equal to 300 kelvins, as it is defined in
If you open that menu.
Okay, just a moment. If you click on the heat structure, here is the axial nodes and surface boundary conditions. If you click here, on the right side you have outer surface and on the left inner. So inner surface boundary conditions will be as the outer surface boundary conditions of the pipe when we connect it. But for the outer surface, we need to just select all the cells, all 20 cells, and then in this boundary condition section, you click here and choose a constant heat transfer coefficient. So then again, sink temperature is atmospheric air, 300 kelvins. Heat transfer coefficient should be around 7 watts per meter square per Kelvin. 7. So then we can define outer boundary conditions for all the cells for the outer heat structure. And just press OK. Then we need to connect our heat structure to the pipe the same way as for all other components. Here also plane along Z direction, surface inner in this case, starting cell and so on. We can leave it as a default one since it is connected for the whole pipe length, and then just press OK. Now, if you click on the heat structure and go to the surface boundary conditions, you will see that inner surface boundary condition is a pipe. Cell 1, cell 2, 3, and so on, until cell 20. So, but heat structure is just a material structure which can provide heat to the in our case to the coolant, but it is just a metal structure. Now, we have to define the power connected to the heat structure. We need to define how much power generated in this heat structure. If you go here, there is a power component. We've extended here the powers. You just need to right click and press new. So you have created the power module, let's say power module, and so then we need to modify it. In our case, the power option is equal power. Sometimes when you need to simulate again reactor core, you need to make kind of realistic behavior. It will be like table lookup power when you calculate the reactivity coefficients and change of power manually for like investigation of the step change and so on, and all other options. There are also options for the reactivity coefficients, but it has to be modified in the root folder on the trace to see these options. But still, we need to choose the powered components. We need to power the internal heat structure here, structure number 40, we just click here, and we have a choice between two heat structures, number 40 and number 50. So 50 it is a glass tube, so in our case it is number 40. Just select heat structure number 40 and press back direction arrow. So now this heat structure is powered. It has to change the color already. I think it has to be green. So then you can see that this component is powered. So usually for the heat structures or heat structured pipes, the color is red. But for the power components, it is green.
Professor, could you go up to where we can find the power?
Here on the left side, the power component is powered. If you click, you can create a new one. When you created the power component, you can choose the powered components, which one you need to define. And here you have to just click on the correct one, heat structure number 40, it was on top here. If you click on that, click on this arrow, it will be powered. So then the power component is connected to the heat structure component. Okay, and close. We also have to define some parameters for this power component. First of all, the initial power, it is a constant one. In our case, it is 1000 watts. And here you see that for them, if we simulate the direct code, we can also define the pitch ratio, uncracked fraction, and also the power exponent, and also a lot of parameters depending on the hour shape. Also, we can define the power shape. For our case, as you remember, we have an unheated surfaces, unheated fraction of the heat structure. So then we need to define like power shape option as a constant axial and radial. In both directions, the power will be supplied to the heat structure uniformly along the whole volume. But here for radial location, you can see that it is equal one to all the radial nodes, radial location of the fuel rod. Actually, it can be defined more precisely. In our case, it can be, since it is a metal structure, so it can be one everywhere. And then to define the unheated fraction, we just need to go to the constant power shape. You will see the table. Here we will have 22 nodes. It is just because we define the option for the fine mesh reflood model. It divides some nodes into the separate cells. So then we can assume like this parameter is the location. It represents the middle point of each cell. That's why it doesn't start from the zero. So it divides the first three cells, as far as I remember, and the last cells. So then we have a kind of node, and it is divided into two parts, and we take the point exactly at the middle. So since, for example, here 0.41125 meters, since it is a middle point of the cell, we can assume that the next cell is already heated, because first 470 millimeters are unheated surface. So then we can define an unheated surface for the first 5 axial cells. And we can just define it as 0. It is an unheated surface. Also, 0.47 plus 1.55 will be 2 point something. So then we can say that for the last 2 cells, it is also 0. would even say that for the cell 20 is 0 and 150.
Okay.
Yes.
So final
Last three
results.
cells are also unheated in this case.
Yeah.
Then just press OK. So actually, model should be ready now. I can just check. Yeah, there is no errors, no warnings. So nothing what could lead to any mistakes or fails of the calculation. Probably everything is defined correctly. So then the basic stuff you need just to check. Just to check the job streams and if the trace module is connected. Like here, I have not defined the root folder. Define it. So define the root folder, then run the simulation. So unfortunately our time is gone, but everything is described. Is described in assignment instruction. So then there is not a step-by-step solution, but at least it says which parameters you need to analyze. So you will have to analyze the quench from propagation in the time. So then for the different time periods, you just define, there will be an option for the instructions, lower and upper quench front. So you just represent it graphically for the different time steps. Well, not the time steps, different time periods. And it will show you how it propagates along the time. You will have to include this into a report. And also the temperature of the fuel, but it is everything is said is described in the assignment instruction. Fuel rod temperature, maybe void fraction you can analyze as well. What else? You can analyze even the pressure. But since we have constant boundary conditions with the atmospheric pressure, it will be more or less the same. So okay, then we can stop for today. If you have any questions, you can ask.
So where do we input the coolant mass flow? Is it from the fill?
Yes. One thing I really forgot to define is in the fill component, here is the initial coolant mass flow.
Okay.
There are two options. You will have to provide two simulations with the different mass flows. It is in the grams per second.
And
just
16.
convert it into kilograms.
Yeah.
And run two cases and analyze them. You can.
So we just change it in the initial coolant mass flow?
Yeah, initial coolant mass flow.
Because it's constant. Okay.
Yeah, it will be constant, 0.01.
0.08.
And the next case is 12 grams, I think.
Yeah.
16 grams per second. So we just run it for two cases and see how it behaves for the two initial conditions for the inlet. It will mostly affect on the fuel rod temperature and the speed of quench from propagation. The higher flow rate, the faster it will flood the system, the faster the quench from propagation. So also, since the mass flow rate is higher, cross section is the same, the speed of the coolant is also higher. Reynolds number higher, Nusselt number higher, so then the heat transfer is more intensive. You can also write this in the report when you will have to explain why. Probably that's all. Actually, if you have any question, we probably have a exercise session next week.
Yeah, yes, we should.
So you will be able to ask these questions there. Also, you can send an email.